Covalent bonding, part 6. Intermolecular forces, which are also known as van der Waals forces because they were named after the scientist who first came up with the concept. We're going to take a look at the three main types of intermolecular force: hydrogen bonding, dipole-dipole interaction, and London dispersion force. Some people would just call that dispersion force. It should be noted that intermolecular forces are not chemical bonds. Chemical bonds are the attractive forces that occur within molecules. They hold the atoms together to make up the molecule. Intermolecular forces, on the other hand, are forces of attraction between molecules. They are many orders of magnitude weaker than chemical bonds. However, they are very important in determining the macroscopic or large-scale properties of covalent compounds, properties like melting point, boiling point, etc. While there are several types of intermolecular force, we're going to consider the three main types here. Dispersion force is important for nonpolar molecules. Dipole-dipole interaction is important for polar molecules. And hydrogen bonding is important for water and biological molecules, molecules like proteins or DNA. I put bonding in quotation marks here to emphasize the fact that this is not really a chemical bond. It's kind of an unfortunate name that we have here. It really is an intermolecular force. Now, the weakest of these is dispersion force, and the strongest is hydrogen bonding. Let's consider each in turn, starting with the easiest, dipole-dipole interaction. Polar molecules have permanent dipoles. The negative dipole of one molecule and the positive dipole of another molecule attract each other. Of course, opposites attract. Consider that with HCl. Hydrogen has a single polar covalent bond with chlorine in this molecule. We indicate the polarity across the bond by putting the delta minus by the more electronegative chlorine and the delta plus by the less electronegative hydrogen. Now, because this is an asymmetrical molecule, or an unbalanced shape, and because it has a polar bond, we can say that the molecule itself has polarity. The polarity of the molecule is indicated with this arrow. It points to the negative dipole of the molecule, with a plus sign on the tail of the arrow indicating the positive dipole of the molecule. Notice that the negative dipole of this molecule attracts the positive dipole of that molecule. Dipole-dipole interaction occurs when oppositely charged dipoles on these molecules, or any molecules with permanent dipoles, attract each other. Well, that's pretty straightforward. So let's consider hydrogen bonding next. This is the strongest of the intermolecular forces. It's really just very strong dipole-dipole interaction. Now, this occurs between molecules that contain bonds, very specifically between hydrogen and nitrogen, or hydrogen and oxygen, or hydrogen and fluorine. This type of intermolecular force is so strong that we don't really consider it to be dipole-dipole interaction anymore. We put it in a category by itself and we call it hydrogen bonding. Let's consider how that works with this example, water. In a water molecule, the hydrogen and oxygen is bonded with a polar covalent bond. We put a delta minus by the oxygen and a delta plus by the hydrogen, indicating the polarity across the bond. And because this is an asymmetrical shape, it's a bent molecule, the entire molecule has polarity, and we indicate the polarity across the molecule by using this arrow. Notice that the negative dipole of this molecule attracts the positive dipole of that molecule. And we can represent the hydrogen bonding, we often see it done this way, with a dotted line between those two molecules. So what makes that so strong that we put it in a category by itself? Why don't we just call it dipole-dipole interaction? Well, it turns out that hydrogen is the smallest atom, and it contains only one electron. So in this bond, where hydrogen is sharing electrons with the oxygen, there is a low distribution of electrons around this nucleus, leaving an almost bare nucleus. And there are no core electrons to be had with a hydrogen atom. It only has one electron to start with. So we have, again, a relatively bare nucleus. That's going to create a very attractive positive dipole here. Now also consider that nitrogen, oxygen, and fluorine are all elements from the upper right-hand corner of the periodic table. That means because they're in period 2, they're very small and they're highly electronegative. So consider this oxygen right here. Not only because it has a big electronegativity will it have a large distribution of electrons around it, but it will be a relatively small atom, and that will allow this hydrogen from this molecule to get close. So because of those characteristics, hydrogen bonding is a very strong intermolecular force. So you should keep your eyes out for HN bonds, HO bonds, and HF bonds. If you see those bonds within a molecule, there would be hydrogen bonding intermolecular force that exists between those types of molecules. All right, now the third type of intermolecular force we're going to consider is actually the weakest of all. This is dispersion force, also called London dispersion forces. An American scientist around 1930 named Fritz London came up with this. For the longest time, it was a mystery as to why nonpolar substances could be liquefied or solidified. What type of attraction was going on between nonpolar substances, since they wouldn't have any dipoles? So what we came up with is that the electrons are always moving within a molecule, and electron movement in nonpolar molecules causes momentarily uneven dispersion of electrons, which creates transient, or some people call them temporary or instantaneous dipoles. Consider Cl2. This is a diatomic chlorine element. So chlorine is bonded to itself. Now you would say that when an element bonds to itself, it would be perfectly nonpolar. But consider that because the electrons are moving, there might be a moment in time where the electrons would distribute or disperse to one side of the molecule. And in that moment of time, there would be a temporary or instantaneous or transient dipole that would be established. So we'd have a delta plus or a positive dipole on this end of the molecule, and then this arrow would point to the negative dipole on the molecule. That would be delta minus. That would be another way to make that notation. Notice that that temporary dipole that's negative from this molecule could attract a temporary dipole that's positive from that molecule. That's dispersion force. Now that could happen when the electrons shift to one side or shift to the other side of the molecule. So because the electrons are shifting back and forth as they move around, we get overall nonpolar molecules. Now the more electrons that are there, the more that shifting of electrons would have an effect. It's kind of like if you have water in a bucket and you're standing still, the water is evenly distributed in the bucket. But if you start walking, of course, as you're taking steps, the water is going to slosh back and forth in the bucket. And the more water you have in the bucket, the more the water is going to slosh back and forth. Molecules that have more total electrons have more momentarily uneven dispersion of electrons, which creates larger temporary dipoles. We can say that more total electrons in a molecule means that the molecule has more polarizability. Now that's kind of a large term, but the concept is pretty easy. It just means that the electrons can have more uneven dispersion momentarily in that molecule. And that would create stronger dispersion forces or more attraction between those molecules. Now this helped to clear up a mystery that existed for some time with the group 17 elements that form diatomic molecules. We call these diatomic elements. So in group 17, we have fluorine at the top of the group, chlorine below that, then bromine, then iodine. And they all form two atom molecules, F2, Cl2, Br2, and I2. And the mystery was, how come fluorine and chlorine are gas at room temperature, but bromine's a liquid at room temperature and iodine is a solid at room temperature? Well, you can take a look at the total number of electrons in the molecules, and knowing that if we have more electrons, there's more polarizability or more tendency to have a larger uneven distribution of electrons momentarily, and that would create stronger dispersion forces or more attraction between the molecules. Consider that fluorine is element number 9, so F2 would have 9 electrons and 9 electrons, or 18 electrons. Chlorine, element number 17, means that chlorine with 2 molecules, Cl2, would have 34 electrons. Bromine is element 35, so Br2 would have 70 electrons, and iodine is element 53, so I2 would have 106 electrons. Notice the increasing number of electrons. That means increasing attraction due to more electrons, meaning more polarizability and stronger dispersion forces with those molecules. So we see gas, gas, liquid, and solid. And what's more, we would see, remember that we said macroscopic properties were affected by these forces. We would see increasing boiling point. So the boiling point of chlorine would be bigger than that of fluorine. Liquid has a boiling point that's above room temperature, liquid bromine does, so that means that bromine has a larger boiling point than chlorine does. And iodine not only has a larger boiling point, of course it must have a larger melting point because it's already solid at room temperature. So we can make predictions that when molecules have stronger attractive forces, it's harder to get them to boil and it's harder to get them to melt. Now, if you understood what we went through in this video, you should be able to answer these 5 intermolecular force questions. Number 1, which intermolecular force is strongest? Number 2, which intermolecular force is weakest? Number 3, which intermolecular force is important for the chemistry of DNA? Number 4, which intermolecular force is the most important in polar molecules? And number 5, why is I2 a solid substance at room temperature? Good luck!